Welcome to the third lecture in a series discussing mitral regurgitation. With this particular lecture here, we'll explore the various forms of qualitative analysis and then combine these along with quantitative analysis forms to allow a greater understanding of what's actually going on with the valve. So with these, there are limitations and considerations that we must have for both methods in determining mitral regurgitation. We can look at the colour flow profiles. When a valve leaks, the regurgitant jet creates Doppler shifts from the movement of red blood cells. It is, however, not only the flow itself, but red blood cells adjacent to the flow that are dragged into the flow, effectively making the jet appear larger than what it really is. This process is called entrainment and is typically seen on centrally directed jets. An opposite effect is seen with eccentric jets. When an MR jet hits the wall, the flow splays out. The blood that is present between the jet and the wall also has a pulling effect that makes the jet want to adhere to the wall. These jets dissipate their energy rapidly and look less severe when visually assessed. And here we have an example of mitral valve failure with the eccentric mitral regurgitant jet. The jet hits the wall and smashes it and then runs along, and it splays out like if you were to get a hose and then point it at the ground, the water would splay out. And so in doing so, it looks much less impressive if you got the hose and you squirted your friend 5 meters away. So we can look at the various forms of qualitative analysis, such as with color Doppler. The duration and size of the MR jet seem to estimate severity. It is important to have the correct gain and correct scale settings on your system. And inappropriately high or low settings will make the jet difficult to assess, and in some instances, not seen at all. Frame rate is also particularly important with colour, as the system frame rates drop dramatically when colour is turned on. It is important for the user to minimise the width and the depth of the box and apply a zoom or TD suppression to raise the frame rate. The minimum we want to have is 20 Hz. Below this, flow is not represented well and the playback may appear jerky. Plus, some flow may even be missed completely. We must always be wary of heart rates. At a high heart rate, the flow may appear underwhelming. Narrow the colour box and use a small field of view and attempt to keep the frame rate up, and this way we can interrogate it better. The frequency may be adjusted on some platforms. Moving the frequency down will increase the Nyquist limit and minimise the aliasing that we see with fast-moving jets. As with colour, the same machine settings apply for pulse wave and continuous wave Doppler. We also may assess the receiving chamber size. A chamber may be significantly dilated if the MR is chronic and the flow is significant. These are apparent in typical volume overload patterns. In the application of continuous wave Doppler, the user compares signal strength or forward flow compared to the right regurgitant flow. A high density signal comparable to the forward flow indicates severe MR. We can look at the maximum flow velocities forward through the valve, and the duration of flow may be increased when MR is significant, as normal stroke volume with the additional regurgitant volume must move through the valve. These will be influenced, however, if there is coexisting significant aortic regurgitation. It is important to view the shape of the MR profile. Severe mitral regurgitation shows a V cutoff pattern due to rapid pressure equalization between the left atrium and the right ventricle. And this is due to the abrupt cessation of mitral regurgitant flow because there's no pressure driving. Systolic flow reversal in the pulmonary veins may show in severe mitral regurgitations. The atria fill in systole, so typically there's forward flow in this period. It is important to note, however, that when the jet is eccentric, it may not be forced down the pulmonary vein and therefore not really identified. The user must also be careful to position the sample volume and in the pulmonary vein. It doesn't matter if it's the left upper or the right upper, and not in the left atrium itself or in the aorta, which can actually move through very close behind the left atrium. Color flowing may be also used to demonstrate duration of flow and estimate severity. This method is also very useful in demonstrating diastolic mitral regurgitation, which occurs when complete heart block is present. Left ventricular systolic function should be hyperdynamic with severe mitral regurgitation for the proper forward flow to occur. If the ejection fraction is below 65%, we actually suggest there is significant LV dysfunction. And in our diagrams here, we have the typical V cutoff type pattern. So instead of the normal parabolic kind of shape that we'd see with the MR jet, we've got very much a tapered point, particularly on this side here, the deceleration side. So as the pressures equalize very rapidly between the left atrium and left ventricle from the torrential amount of MR that's moving through, the driving force is gone, so the flow stops. And on the one on the right here, we've actually got our sample volume placed in the pulmonary vein. So what we'd expect to see is an S component, a D component, and then an atrial reversal. But in this instance here, we have a reversal flow in the systolic component. And that's because the mitral regurgitation is rushing down the pulmonary vein when it should actually be filling. Then we can start to look at quantitative methods. We have the vena contracta, which measures flow as it moves through the valve. The point of measure is just distal to the regurgitant orifice. The larger the distance, basically the greater the severity. There can be issues with this method though when the calcification of the leaflet tips is present, which may make it difficult to accurately place the caliper points. There may be multiple orifices where the flow originates. Also, color pixels may, because they're actually larger, may blend together and effectively make the flow look larger than what it really is. We can also look at jet area to LA area. The user performs a trace to get an area of the left atrium and then basically does the same again for the regurgitant jet. The greater the jet ratio, the greater the severity. Note, this is only effective when the jet is not eccentric and hits a wall. As mentioned previously, these jets splay and dissipate their energy rapidly. So we can also look at the table that we have here, according to our severities, mild, moderate, severe. So as the vena contracta gets larger, of course, it's more severe. When we have a jet area to left atrial area of less than 20%, we know it's mild. It's a little bit variable when it comes to moderate gradings, so there's no real kind of cutoffs there, but it's somewhere in that range between the 20 and 50. But we know above 50 is basically severe. So how do we go about determining regurgitant severity? We know our flow calculations revolve around the simple principle of the conservation of mass. Simply put, we refer to what goes in must come out. So as we'd expect, the stroke volume between two cardiac valves is equal in the absence of an intracardiac shunt or regurgitation. In regurgitation, the stroke volume through an incompetent valve is increased. It's the sum of normal stroke volume plus the volume of blood that has leaked backwards into the receiving chamber that then needs to be expelled forward again. So we can see our volumes here. So the regurgitant volume is going to equal a competent valve plus the regurgitant volume. So we just rearrange our formula slightly because we want to work out what the regurgitant volume is. So it's the difference between the regurgitant valve and the competent valve. It is therefore important that assessment of the competent valve must not leak. To do so would distort our calculation. Viewing the calculation above, we can see a larger competent valve would lead to the regurgitant volume being reduced. We can have a look here with our mitral regurgitation. So a couple of points that we may actually use is the stroke volume through the mitral valve and then the stroke volume through the LVOT. Typically, we like to use the LVOT because it's an easy point to actually measure. But as we said, if we had aortic regurgitation, we wouldn't be able to use that valve. If the valve did actually leak, we could substitute with another point of easy measure. And typically, we'd use something like the right ventricular outflow tract. Typically, the tricuspid valve is not preferably used because it's difficulty in measuring it and the lack of reproducibility in getting that diameter right. This can then lead to significant error in our calculations, so something we really want to avoid. So if we put it all into practice, here's our mitral annulus that we've measured at 3.5 centimeters, and we've measured the VTI for the inflow at 11.2 centimeters. We measure the LVOT diameter at 2 centimeters and the left ventricular outflow tract VTI at 13.4. So throwing it all in, we get our stroke volume through the mitral valve 108, and our stroke volume through the LVOT 42. Simply minus the 2 and we get 66 mils. So important with this particular calculation here is all our units were already in centimeters. We didn't actually need to apply any conversions to the units. Of course, we always come round to our limitations, assumptions, and considerations. And I go over it again because the more times we can go over this, the easier it seeps in, and then we can learn the basic principles behind it. So we know that our principles are based on a simple hydraulic formula that says uniform flow occurs within a cylinder. So for this to occur, we have the assumptions that the cross-sectional area remains constant during the period of flow, the cross-sectional area is circular in shape, the sample volume remains unchanged in relation to the surrounding structures, and the flow is steady through the cross-sectional area. As we explored earlier, we understand that flow profiles may change during the period of flow. The cross-sectional area may also change through the period of systole or diastole, and the cross-sectional area is not always circular. Plus, the sample volume used to measure may move, or the heart may move while the sample volume is constant. There's potential area in measuring the diameter, which is used to derive the cross-sectional area. A small under or overestimation can have a significant impact on the stroke volume result. The result may be compounded as there are now two sets of stroke volumes that are calculated this way. So here we have an example of our mitral annular diameter, and if it was actually if we measured 4.0, but the actual was 3.7, we could see there's a significant error of 20 there between the two. Prominent errors may also occur when we derive the VTI. An ultrasound beam that does not have parallel alignment underestimates the true velocities of the flow. The sample volume may be placed incorrectly, such as with the LVT when it's too close to the aortic valve. There are systolic clicks and flow acceleration occurs as flow converges to the orifice. Conversely, if it's too far away from the valve, the user will obtain LV systolic flow at the basal level. For atrioventricular valves, some users inappropriately place the sample volume at the leaflet tips rather than the annulus, and this is our point of measure. Issues may occur with the VTI tracings. The user may poorly follow the edge. The user needs to follow the motor velocity for pulse wave typically, and the leading edge for continuous wave. The Doppler scale may be set too low, with the flow extending off the screen and some velocities lost or mingled with aliasing velocities from flow in the other direction. Or it could be set to too high, with very small velocities represented on the screen, and the flow is then very difficult to accurately measure. Forward stroke volume through another valve also cannot leak. The valve must be competent, as regurgitant flow increases the forward stroke volume through that valve. Looking at our formula, it is seen this would lead to an underestimation of the regurgitant volume of the valve we're actually interested in. Similarly, an intracardiac shunt will have the same effect. If the valve is measured distal to the shunt, and thus has greater stroke volume, again the regurgitant volume calculated would be underestimated for the valve of interest. Finally, we must be aware that there's beat-to-beat variability. Even in someone with sinus rhythm, there are slight deviations in heart rate, and therefore stroke volume with associated slightly variable ventricular fillings. Multiple tracings are required in most cases, even with someone that has sinus arrhythmia, atrial fibrillation, ventricular bigeminy, and so on. We need greater numbers of measures to accurately average and represent the average stroke volume. It must be noted, despite the best efforts of a sonographer, that even when measuring competent valves, so both points that didn't leak, a regurgitant volume may be evident. The grading of severity that we have are set with standard deviations of 95% confidence, so we minimize the possibility of a normal valve being classified as having anything more than mild regurgitation. So in summary, there are a variety of qualitative and quantitative analysis forms that may be utilized in our assessment of full mitral regurgitation. The greater the complement of tools used, the greater the diagnostic calling confidence we have in the result that we derive. Many of the methods have considerations to be wary of. The astute sonographer will know when not to apply a method or modify their acquisition to minimize these unwanted effects. And the regurgitant volume calculations revolve around the frequently explored stroke volume method. Having a firm grasp on these will aid in all areas of a hemodynamic understanding.